Okay, remember, no class Thursday or Friday this week, anywhere, because faculty have professional development. So you only have one more day this week and you're done. And then next week, and then spring break. What's that? Well, yeah, I'll see you next week. Yeah, but in other words, the last class you'll have, yeah, you won't have me on Thursday. The last class you have this week is tomorrow, and that's it. It's a short week for y'all. Yeah. And we have to drive all the way to Irving for our 2-day conferences. I think they feed us, but if I don't drive that far, I can always just stay here and eat at home. So, all right. We're now going to find derivatives of functions without having to do the epsilon delta proof or the limit using Riemann sums or whatever. Now we're going to start getting into the shortcuts to the definitions of what these things really mean. The functions we're going to look at this time are constant functions, power functions, polynomials, exponentials, rationals, and combinations of those. So the first one we're going to look at. A constant function. So let's pretend our function f of x is some constant number, c. What does that mean? What does that mean? How would you read this? But how do you read it? It represents a derivative, but how do you read it? Because this thing tells a whole bunch of stuff what you have to do. Because as we go through this course and in calculus 2 and 3, we're going to start changing. It won't always be dx on the bottom. Or I might have multiple dx, dy, dz on the bottom. This is the derivative of the function f of x with respect to the derivative of the x variable. So in other words, what you're going to look at here is in a function, the only thing that you're going to differentiate is the parts that have x. Because what does a derivative find? It finds a slope. So the derivative of this function, what's another way of writing the derivative? We could simply write f prime of c. And there are a whole bunch of ones. I gave you those last time. We could use any one of those. So the derivative of a constant function is what? No. Y0. No slope. It's a horizontal line. Because if you graphed this function, it would simply be a horizontal line going through C. It has no slope. And you could, if you wanted to, you can use the limit. As x goes to infinity, we have f of x how would you do the limit of this function? What would you put together to find the limit? How have we done it in the past? Last couple of sections, how do we do it? No. You're supposed to look at your notes at home. Because what we do, the slope is defined by this equation. What is that equation called? It is a quotient. That's not the name of it. Difference quotient. That's the name of it. Because quotient simply means fraction. Yes, it is a fraction, yes, but it's a difference quotient. This defines our slope. But we have to do something else. We'll end up with an h. How do we get rid of the h? What do we put in front? The limit as h goes to what? 0. Because h is the distance from x1 to x2. This is your formula. This gives you f prime. So you see now why once we start learning these shortcuts, we don't have to prove it anymore. So, because if you look at this one, the limit as h approaches 0, what is the function? We're looking at this one. What is the function? C. And since there is no x, we can't put a plus h. The function itself is c. So we got 0 over h, which is 0. So we didn't have to take this because it goes to 0 automatically. So that's what we're looking for. That's what we're looking at this equation now. Remember earlier, also, we did rationals or radicals. What was the derivative of that function? And how do you figure it out? How did you figure it out? And it's only part of it. It's still wrong. Negative 1 over x squared. But how did you figure it out? Use what we just talked about 5 seconds ago. 1 over x plus h. Keep on going. It's not done yet. You forgot the whole limit part. Because if you don't, you'll still have x's. Okie doke. Let's go. We just survived. Actually, somebody told me that was not a drill. So it was an actual fire in one of the places, one of the labs. So that's why you should have taken your math sheets with you. That could save you. What if it was raining out there? Walk by there. Let me help you out. Okay. So yes, we could do it this way. And the way we would do it after this would be they both need a common denominator. So this would be x over x. This would be x plus h over x plus h. And you see all the work you're going through. This brings us to, besides the constant rule, the first rule we talked about is this is our first one, which says if you have a function that's a constant, the derivative of it is 0. That's the first rule. Now we're going to look at something called the power rule. That is our second one. The power rule. We just saw, we didn't finish it, but we know what's supposed to happen in there. The power rule says this. If you have a function, if f of x equals x to some power, The derivative of it is bring the power down and subtract the power by 1. And that's your derivative. Let's see how we would do this one. If you have a function like this, we would rewrite it using the rules of exponents. So then the derivative of this function using the power rule, bring the power down, which is -1, and subtract 1 from the exponent, according to this rule right here. So that would be -1 x to the power -2, which means -1 over x squared. Now you see, I told you earlier that once you start doing the shortcuts, this saves us about 20 minutes of work and the chance of making a mistake. Because if we have to do the 1 over x plus h minus 1 over x over all this over h, we have a lot of work. And the bigger x is, the more work we have to do. So this is the shortcut. Also, if we had a function that looks like this, let's combine what we've done so far. So the derivative of this function, wait, again, let me take you back now. How would we solve this using the limit formula? We would have to take x plus h to the 4th power, x plus h times x plus h times x plus h. This now saves us time. So what happens here? We have the constant coefficient in front, leave it alone. What's the derivative of x to the 4th? Bring the power down. So it's 4x and subtract 1 to the 3rd. So this part is 3 times 4 is 12x cubed. The next one, there's the constant coefficient. Take the derivative of this one, bring the 2 down. Subtract 1, so we have 1. So 2 times 2 is 4, x to the 1st. What's the derivative of this function? Of that term? 0. It's a constant. -1's a constant. There's no x, so it becomes 0. So there's your derivative. And the beautiful thing is, once look at the example sheets. Here you go. Look at your example 1. Let's look at some of those. Find the derivative. What's the derivative of this one? 3x squared. X to the power 2/3. What's the answer? Yeah, bring the power down. So it's 2/3 -1/3. Because 2/3 minus 1 is 2/3 minus 3/3. 2 minus 3 is -1. So our final answer for this one is 2/3 to the power x to the power 1/3. Or if you, again, now we're ideally supposed to rationalize our denominators if we have radicals on the bottom, but I think they'll take it up. They'll take that. So you'll first see if they'll accept this one. If not, then put this one. If not, then put this one. If not, then simplify it. I hope you all remember how to rationalize denominators. What would I have to multiply to this one? What's that? Nope. To rationalize this one, we know we have a cube root. How many x's are we missing? We have how many here? We have 1. How many are we missing? We need 3 of them, so we need 2 more. So the answer would be that. Again, it's the algebra that's going to hurt you, not the calculus. The calculus part is just the first step. The algebra part will hurt you. X to the power radical 2. What does that one become? Yeah, because we're looking at f to f prime. That's what this whole thing's doing. So what's your answer? It's only 2 steps, ladies and gentlemen. What's the first thing you got to do? Bring down the exponent. And then subtract 1 from the exponent. There you have it. That's all you need to do. The square root of 2 is going to be at 1 point something, a decimal. So leave it like that. D, 1/x to the 4th. What is its derivative? What's the first thing you got to do? Bring it up on top. How do you bring it up on top? What does it become? It's a -4. Bring the exponent down and subtract 1. which becomes -4 over x to the fifth. E, x to the power -4/3. So what's my coefficient? Yep. Bring the power down and subtract 1. So it becomes what? Since the original question started off with a negative exponent, might as well leave it as. Even though the rules of math said you're not supposed to. You never want to have a negative exponent as your final answer. Not only that, but how would this simplify? How would you simplify this equation? What does it mean when it's negative? It goes on the bottom. So on top, we have what? -4. Very good. What happens with that one? What is 7 divided by 3? It's an improper fraction converted to a mixed number. What does it become? How many times is 3 going to 7? With how many left over? So this one becomes x squared, x to the power 1/3. Rationalize the denominator. What do we have to do? By what? Right. Because we need 3 of them. We only have 1. So we have to multiply top and bottom by cube root of x squared. We need 2 more x's. This gives us just x. So our final answer is that. You have to know how to simplify equations. The reason being because even though this author or this software that we use may not require you to simplify it, the common conventions of math around the world says you cannot have a radical on the bottom. And you cannot have a negative as a radical answer, as an exponent. So you have to know how to do the algebra to simplify all the way to the end. And the last one, F. It is square root of x2 plus pi. What do you think you have to do here? What have we done with all the other radicals? How can you rewrite that? So we could do the same here. So this becomes x2 plus pi to the power 1/2. What are the rules of exponents? What do you do when you have a power to a power? Multiply. Because this is over 1. So 2 plus pi times 1 is 2 plus pi. 1 times 2 is 2. Now we can take the derivative of it. 2 plus pi over 2. 2 plus pi over 2 minus 1. Can we simplify the top, the exponent? We got 2 over 2 plus pi over 2 minus 1, which is 2 over 2. 2 over 2 minus 2 over 2 cancel. So our final answer is that. Yes. Again, I'm not going to stop saying this. It's the algebra that's going to hurt. You have to have a very, very strong algebra sense to do this. Because what part of this whole thing is calculus? Just starting the whole thing. That's because really it's all algebra. Algebra, calculus is simply a turbo algebra. We'll just do things a lot faster. But you still have to know how to do it. When you get ready to take calculus 2, you have to know your trig functions, your hyperbolics, your inverse functions. So again, start brushing up on those. But whenever I teach those, I make sure I go through those first couple of weeks. So I don't start my Cal 2 class until like the second or third week because I make sure everybody knows the rules of algebra and trigonometry. All right, there's a good example too. A, find the derivative of this. If y equals that, what's the derivative? Because we have the constant coefficient, the 3, bring down the 2, and subtract 1. So we have 3 times 2 is 6 to the x to the first power. Part B is just an example of saying the negative of a function. Basically, what this one's saying, if your leading coefficient is negative and you take the derivative, leave the negative out in front. You don't have to do anything with the negative. All you have to do is worry about this. And the negative will stay out in front. That's pretty much all it's saying. So the way they wrote it is the derivative of a negative function with respect to x is the negative of that function with respect to x. So if your function is negative, just you can factor out the negative out in front. This is also when we start doing the opposite direction, when we start doing integrals, you can take out the negatives also. We have another example, 3. We'd still be working on that x to the 4th question using it says, example 3, find the derivative of the polynomial y equals x third plus 4/3 x squared minus 5x plus 1. Find the derivative. So the first one, how many terms do we have here in this equation? 1, 2, 3, 4. So we do all 4 of them separately because it's the sum and difference rule. This is what we call this. It's the sum and difference rule. Whenever you're separated, treat them all separately. So what's the derivative of x cubed? Bring the power down and subtract 1. The next one, we have the constant coefficient. What's the derivative of x squared? Bring the power down, get 2, subtract 1. What about this one? What's the derivative of x? Why 1?
Well, isn't it x to the 1?
It's x to the first. So if you bring down the 1, we get a 1 there. And then subtract 1. 1 minus 1 is 0. X to the 0 is what? Check your key. You check your key swiping it? Okay. Hold, let me. No worries. Three x squared. 2 times 4 is 8 over 3 x minus 5. And there's your first derivative. Let's look at example 4. Remember, the first derivative, recall, the derivative finds the slope. Now, this will help us with the next one, understanding that concept. Does y equal x to the 4th minus 2x squared plus 2 have any horizontal tangent lines? What does that mean? Does the function have any horizontal tangent lines? What does horizontal look like? Yeah, it's the horizon. So what we use this for is what this is really looking for vertices. If you think about it, if we have a curve, let's say we have a cubic function, where's the only place that we have horizontal tangent lines? Remember, what does tangent line mean? Touches at only one point. That would be here, because the horizontal tangent line does that. That would be here. The horizontal tangent line does that. So we're using the derivative now to find vertices, which we couldn't do in algebra. So how do we find this? How do we answer this question? Does this function have any horizontal tangent lines? What's the first thing we have to do? I'll put the steps here. It's not that many. First step, find the derivative. Okay, so what's the derivative? What's the derivative of x to the fourth? 4x cubed, right. Minus the derivative of 2x squared, 4x. And that one disappears. Okay, so we found the derivative. Now what? No, that's what this already is. That's what this does for us already. Because the horizontal line has what slope? The horizontal line has slope 0. So we set the equation equal the derivative set it equal to 0 and solve for x. Those are the x's where the vertices are, the highest or lowest points. So how do you solve this one? Can we factor anything out of the equation? What? 4 and an x, which leaves us with can we factor this one any further? Obviously, since I put parentheses there. So what is x squared minus 1? What does that factor out into? Very good. It's the difference of two squares, x plus 1, x minus 1. It's a difference of two squares. Very good. For some reason, this equation baffles more students. More errors occur with that one than anything else. So at what are the x's where we have our vertices? So what are the x's that make it equal to 0? Okay, take each of these, set them equal to 0. What do they give us? Zero, -1, and +1. Because if you think about it, review back in algebra. Okay, we have, what this thing tells us is we have 3 vertices. And they occur at those points when x is 1, -1, and +1. 0, 1. Let's look what this means. Our function was x to the 4th minus 2x squared plus 2. If I asked you just to give me the basic information, what can you tell me about this graph? What's it going to look like? What's the end behavior going to be? What does that mean? What does that mean? Either right, because the degree is 4, it's an even degree. That means the end behavior means they either both point up or both point down. Since our coefficient is positive, they both point up. So we know that our graph will look like that. How many times maximum will it cross the x-axis? 4 times. The degree also tells us the number of solutions we'll have. So what this equation will look like this. It'll have at most 4 solutions because the degree is 4. The number of vertices is equal to n minus 1, which is, we're going to have 3 vertices. One's there, and one's there. And this one's at 0, this one's at 1, this one's at negative. That's what it's telling us. But the actual graph itself, I'm just saying what it looks like. It could be above the x-axis, it could be below the x-axis, but that's the shape of the curve. So that's what that question's asking. Does it have any horizontal tangent lines? Yes. It has 3 of them. 1, 2, 3. Let's see. The next rule. The exponential function rule. What does an exponential function look like? The graph looks like this, yes, always crosses through 1. The answer can never be negative. But what does the function look like? This is the graph. What does the function look like? Right. Any number as long as a is greater than 1 to a power. And that's where the variable is. This time, x is the variable. When x is negative, the numbers get really small. Why? Because if we had 2 to the power of -2, that's 1 over 2 squared, which is 1/4. So the bigger the negative number becomes, the smaller the actual number becomes. So it gets closer, closer, closer to the asymptote 0, horizontal asymptote. The derivative of this function is a to the x. That's the shortcut. What's really happening is this. If our function is any base to some function u, this is an equation of u with function of x. The derivative of that function is the derivative of the exponent times the equation. That's why exponential is much easier than anything else. All you got to do is take the derivative of the exponent, that goes in front. Leave the equation alone. The most common exponential function we have is e to the x. E to the x is the inverse of which function? Right. How do you know they're inverses? Because if I took the ln of e to the x, the exponent comes out front, ln e, this becomes 1, so the answer is x, which is how you prove inverses. Or likewise, if I took e to the power ln x, the same bases, so we just have x. Okay, here's a an algebra review. Write that, expand it as a logarithmic equation. Log base something of something. What is ln? What's that? Nope. Which what? What, this thing? Or is it log base e? Yes. There. Log base 10 is a common log. Whereas if there's nothing there, it's automatically log base 10. Yes. This is the conversion. So if we had f of x equals e to the 3x, what would the derivative be? So du means what? Take the derivative of the exponent. What's the derivative of 3x? 3, and leave that alone. And there's your answer. That's all there is to it. Nope, that's it. No, that's a good question. There's a difference between this and this. This is base x. So the exponent, that's why we subtract by 1. This one, the variable in question is x, and that's, we just do the dx e to the power x. The derivative of x is 1, which gives us e to the x. Where's the next example? 5. Find the equation The equation of the line tangent to the graph of y e to the x going through the origin. Okay, I'll give you all a couple of minutes. What are we looking for here? Equation of the line tangent to the curve. So if we drew a graph, our curve would look something like this. That's this function. Going through the origin. So here's the origin. So we want, it's got to be tangent, so it's got to be touching only at one point. So what do you need to find the equation of a line? What do you need? You need the slope. Slope of what? Where? Because yeah, I mean, it's right. You need slope, but you have to be a little bit more specific now. The slope of what? Where? Hmm? To where? You need the slope of the line tangent to the curve going through the origin. Okay, how do we find the slope of that line going through the origin? So to find the slope, what do we do? How do we find the slope? The derivative, which is e to the x. So this is the slope. We need a, what else? You need a slope, and what else do you need? To find an equation of a line, what two things do you need? Minimum. Nope. You need a point. Do we have a point? The origin. What's the coordinate of the origin? So we have the slope of the line going through the origin. What is the slope? We need to have a number. Do we have a value of x? Right there. So the slope is e to the power 0, which is what? So my slope is 1, and my point is 0, 0. How do you find the equation of a line now? we have the slope. So the y-intercept is 0. And we have the slope. So the equation is y equals 1 times x plus 0, which is that. That's the equation of the line tangent to the curve going through the point 0, 0. So far, so good? Yeah, I wish I didn't take away a lot of our time. I was trying to do 2 sections today because we don't meet on Thursday. Now, the next thing we're going to talk about. The product and quotient rules. Let's look at the product rule first. What does product mean? Multiply. There's an example of the product rule. You have 2 functions multiply to each other. So what this thing says is the derivative of this function, the derivative of x, derivative of p of x over dx. We have to take both of these separate. We have to look at one of them and the derivative of the other. So we have the function f of x times the derivative of g of x. Since it's a product, we're making things bigger, we put a plus sign there. Then the other one, g of x times the derivative of the first one. Let's look at an example here. X plus 2, x minus 5. Yes, on this one here, if you can multiply together and just do the individual pieces, that's a lot easier. And this, we'll do it both ways. We're going to use the product rule for this one, and then we're going to multiply them together and see what we get. We should get the same answer for both of them. If we multiply these together, we get that. So the derivative should be what? Two x minus 3. That's what it should be. So instead of memorizing these rules with the product and quotient rule, I'm going to show you something that's much easier. That's much easier to memorize. You have your original functions f of x and g of x. So it's x plus 2 and then x minus 5. Below there, take the derivatives. So you have the f and g derivatives, f prime and g prime. What's the derivative of f? What's the derivative of x? What's the derivative of 2? So it's just 1. Same thing here. Now, instead of memorizing this thing, because it'll get more confusing when we do the quotient rule, all you have to do is memorize one thing. Start from G and do the fishy thing. It's always going to be the same. Product means you're multiplying, making things bigger. So you're going to add these two. Take G times F prime. So x minus 5 times 1 plus, now we do the other way, x plus 2 times 1. Multiply, we get x minus 5 plus x plus 2. X plus x is 2x. Negative 5 plus 2 is negative 3. It works. But I'm going to give you much more difficult ones in a second. This is Mickey Mouse, and it'll just easy way to show it to you. So again, the product rule, start with your function f, g, then the derivatives, and it's always that fish. If it's product means making things bigger, you're multiplying it, you put a plus. What do you think the quotient rule is going to look like? Again, it's the fishy thingy. Everything's the same, but now when you do quotients, when you divide things, do you make them bigger or smaller? Smaller. So this one's going to be subtraction. So for the quotient rule, we're going to have G times F prime minus F times G prime. But there's one more thing. Remember when we had the function 1 over x? The derivative of it became what? What was the bottom number of that one? The derivative of 1 over x. What did that give us? Negative 1 over x squared. So notice how we increase the denominator by 1. So with the quotient rule, it'll be that. So this is how your original function will look like. The derivative will look like this. I guarantee this, memorizing this fishy thingy will be much easier than going through all this other stuff. But I'll show you what the quotient rule looks like if we did it the long way. So our function is polynomial is f x over g of x. That's what it looks like. Now you see why I'm saying my fishy thingy looks a lot easier than looking at that crap. Example 6. Find the derivative of y equals 1 over x times x squared plus e to the x. And then b will be y equals e to the 2x. Well, we talked about this one. We should know this one already. What's the derivative of this one going to be? Two e 2x. What goes in front is simply the derivative of the exponent times whatever the original function was. That's the only thing that changes with the e function. That's why you'll learn to appreciate whenever you have functions with e's in them. They're much easier to deal with. So that this one B was easy. Let's look at A. There are two ways you can do it. What are the two ways you can do it? You can't do that. You're multiplying. Right. One of them, one way is you can distribute. You can have x squared over x plus e to the x over x, which gives us x plus e to the x over x. Now, how would you find the derivative of this one? It's the sum and difference. So take the derivative of both of these separately. What's the derivative of x? 1. Now, how do we take a derivative of this? What rule do we use there? What does it look like? What form is this? It's a quotient. It's a fraction. So we got to use the quotient rule. The top is f, the bottom is g. So we got e to the x, x. What's the derivative of e to the x? E to the x. The derivative of x is 1. Do the fishy thingy. Is it a plus or minus? Minus because it's a quotient. So we have g is x times e to the power x minus e to the x times 1. What else? Over the g squared. Because it's g f prime minus f g prime over g squared. So looking at this, we get x e to the power x minus e to the power x over x squared. I thought we were close to a bathroom. No, it is the pipes. They're expanding. So what do we do now? Example 7. What do we do now? We can split up both of these. We get e to the x over x squared minus e to the x over x squared. One x cancels, so we have e to the x over x, e to the x over x squared. And there's your derivative. Okay, that's the first way you could have done it. The second way, we could have done the product rule. We could do the product rule here with both of these. This is A2. Where the first one is F, the second one is G. So we have 1 over x squared plus e to the power x. Again, we know what the derivative of 1 over x is, hopefully by now. Negative 1 over x squared. Derivative of x squared is 2x. The derivative of e to the x is e to the x. Since it's the product, we add. So we have negative 1 over x squared times x squared plus e to the x. That's these two. Plus, now these two. 1 over x, 2x plus e to the x. Now we just do the algebra. Distribute those, get rid of the parentheses. So we got negative x squared over x squared minus e to the x over x squared plus 2x over x e to the x over x. X squared over x becomes negative 1. X is canceled, so we have plus 2. Then what? X squared over dx. Negative 1 plus 2 is 1. Then we have plus ex over x minus ex over x squared. Same thing we got last time. What's our next example? Any questions so far? Example 7. A equals x squared minus 1, x cubed plus 1, e to the power negative x. Again, b, what's the derivative of b? Mhm. So that one's pretty easy. Again, e's are my favorite. We have to use the quotient rule here. All right, let's look at this. So since we have the quotient rule, the top is the f, the bottom is the g. The derivative of f gives us what? 2x. The derivative of g gives us 3x squared. Very good. Since it's the quotient, we have to subtract. Again, the only thing we know for sure is the denominator has to get squared. Whatever's on the bottom gets squared. So on top, we got this first one. We got x cubed plus 1 times 2 of x minus, since it's quotient, x squared minus 1 times 3x squared. These two times minus these two. What do I do next? Factor? Actually, see, can we factor anything? Yeah, let's distribute, get rid of the parentheses on top. Leave the bottom alone. Don't touch the bottom. So on top, we got 2x times x cubed is x to the 4th plus 2x. Minus 3x squared times x squared is 3x to the 4th minus 3x squared. I'm just doing these two first. And then I'll distribute the negative. So I have 2x to the 4th plus 2x minus 3x to the 4th plus 3x squared. I distribute that negative sign. Whenever you get rid of parentheses, combine like terms. So the highest power, we have 2x to the 4th minus 3x to the 4th is negative x to the 4th plus 3x squared plus 2x. Can we do anything on top? Can anything factor out? A negative x, because we have a negative coefficient. So we have x to the third minus 3x minus 2. Can we go any further? Nothing can cancel. We can't factor this one out because it's a cubic function. There's our answer. Let's look at example 8. Do you need it back up there? Example 8. Y equals x minus 1, x squared minus 2x over x to the fourth. How would you approach this one? Let me save you half an hour of work. Because if you're going to use the quotient rule, that means on the numerator, you'd have to use the product rule to do the derivative. Here is the rule. Whenever you have a monomial on the bottom, multiply the top together and divide each term by x to the fourth. So we got x times x squared is x cubed. Positive times negative is negative. X times 2x is 2x squared. Negative times positive is negative x squared. Negative, negative is a positive 2x. Combine like terms, we have minus 3x squared. Now we take each one of these separately. And divide by x to the fourth. So x cubed over x to the fourth becomes 1 over x. X squared over x to the fourth becomes 3 over x squared. And 1x cancels, we have x to the third. Rewrite the equation that way. Because this becomes x to the power negative 1, 3x to the negative 2, plus 2x to the negative 3. Now we can take the derivative of each one of these separately. The first one becomes negative 1 x to the power negative 2. Let's subtract 1. Minus 3 times negative 2 x to the power negative 3. 2 times -3x to the power -4. Remember, the power comes down and subtract 1. So our derivative becomes -1 over x squared. Negative and negative is a positive 6 over x cubed. Positive and negative is a negative 6 over x4. And there's our derivative. Again, you can use any method you want to, but that should be the answer you come up with. Did I go too fast? Did I confuse anybody? Because I know you're looking at it at how do you get that stuff? Right. I can't speak anymore. I got something in the back of my throat. Yeah, I'll get some later. I'll just sound like a tough cowboy right now. Okay, the last thing. Higher order derivative. This is going to lead us into the next section. When we're talking about movement, like displacement, velocity, acceleration, and because first you have displacement, how far something moves over a period of time. Then the derivative of that is velocity. The derivative of that is acceleration. The derivative of that is called a jerk. It's how fast, it's a rate of change of acceleration. So the first derivative would give us what? 3x squared minus what? 6x and 0. The second derivative the derivative of this one now, the derivative of the derivative. So it would be 6x minus 6. The third derivative would be 6. The fourth derivative would be 0. So we see here the polynomials, eventually they have a expiration date. But if we had a quotient, that would keep on going and going, because the derivative would never disappear. Because the first derivative would be -1 over x squared. The next one would be -2 over x cubed over and keep on going. So that's, I mean, you're not restricted on how many derivatives you can take, only how far the function takes you. And on your sheets, you see the different ways we can represent, which is pretty cool because it's the derivative of x of the derivative. The This is the second derivative. The derivative of a derivative. And that's all for that section. And on the last page, you can see the different symbols we use and how to read them. I was hoping to do two sections today, but since we had that fire alarm, we missed that in 20 minutes. But the next section is just that it's now an application. We're going to look at moving objects. If I give you the position of an object, can you tell me what its acceleration is as it moves? And then we're also going to look at how in economics and business, how we use calculus in that. Okay, everybody.